Hi everyone, I'm Maddie, a first year PhD student at the ANU, and I'm currently on Ngambri and Ngunnawal country. Today I'll be telling you about what I've been working on for the last 6 months, which is chemical abundances in the metal pore globular cluster M22. For this, I've been working with the amazing David Young and Stephanie Monti, along with some other fantastic researchers. So to start off with, what is a globular cluster? Well, if we take a galaxy with a bulge in a disk and embed it in a dark matter halo, globular clusters mostly appear above and below the plane of the disk. These are very old collections of stars, and despite many years of research, we still don't know exactly how they form. We do know that some of the globular clusters were born in the disk and kind of migrated out into the halo, while others came in during accretion events, either as one of the clusters of an accreted galaxy or as the nuclei of the galaxy itself. And unlike a galaxy, which you can kind of categorize based on morphology, you can't say a lot about the formation history of a globular cluster just by looking at it. If I told you that one of these was a nucleated dwarf galaxy, would you be able to guess which one it was? On the right is 47 Tuc, which is pretty widely accepted to be a globular cluster. Whereas on the left, we have Omega Centauri, which we think is the nucleus of a dwarf galaxy which was destroyed by our Milky Way. This becomes more apparent though when you look at the color magnitude diagrams, with Omega Centauri having a wide red giant branch, as well as lots of other weird things compared to 47 Tuc. The moral of the story is though that you need to look at the chemical abundances in order to try and characterize a globular cluster. So I've been looking at a cluster called Messier 22, and this was actually the first recorded globular cluster in Western history back in 1665. It's got an iron abundance of -1.8 dex, and in the late 70s and early 80s, people were speculating that they had found a less extreme version of Omega Cent. And today we're fairly certain that the cluster has an iron abundance spread of 0.4 dex. However, there are some groups which disagree with this, so I can talk about that at the end if anyone is interested. It has also been found to contain 2 S-process element groups. And when I say S-process, I'm referring to the slow neutron capture process, which is responsible for producing elements such as barium, lanthanum, cerium, or neodymium. This occurs in stars near the end of their life, known as AGB stars. And these stars play a very important role in the formation of globular clusters. AGB synthesize a huge range of elements and isotopes. An important one that I'm going to talk about today is magnesium. The magnesium aluminium chain operates by cycling between magnesium 24, 25, and 26. And one of the sources of neutrons for S-process elements comes from a reaction which produces magnesium 25. So if we can observe the isotopes in M22, then we can use this to figure out information about the AGB stars and by extension, how the cluster may have formed. I am going to preface this though with this introduction from Chatrone 1996 in saying that isotopic analysis is one of the most difficult subfields of spectroscopy. And you'll be hearing from Ella a little later on, who's also using this technique, but with lithium. Additionally, being a very old globular cluster doesn't make things easier. And this is the lowest metallicity that anyone's performed magnesium isotope analysis at. So this is an example of magnesium hydride line, and it's got an isotopic ratio of 70% magnesium 24, 15% magnesium 25, and 15% magnesium 26. These 3 isotopes have different electronic transitions and therefore will fall at slightly different wavelengths. There's about 0.08 angstroms different between these lines. And by changing these ratios, you can see how it impacts the line's asymmetry as we increase magnesium 24 to 80% and then 90%. And these are differences that we are able to measure. So here are all the measured stars in M22 from Marino et al. 2011. I'm plotting iron against neodymium, one of our S-process elements. And each of these stars has an error of about 0.1 dex. I want to highlight 3 S-process poor stars, which I'm showing in blue, and 3 S-process rich stars in red. Each of these stars is special because they are the only ones with detectable magnesium hydride lines. And I have UVis data for each of them with a signal to noise ratio of at least 200. Previous studies have tried to fit magnesium lines by hand, but I'm using my code called Ratio to do it for me. Ratio stands for Rapid Automatic Isotope Optimization because everyone loves acronyms. It uses a simple hill climbing algorithm with a code called Moog to perform stellar spectrum synthesis, and then spits out a ratio between magnesium 24, 25, and 26, and the 1 sigma errors are calculated with chi-squared fits. This is an example of just how weak these lines are, but we're still matching the data to 0.01-ish of the flux, which is really good, I think. This is one of the outputs for Ratio. And remember, blue is the S-process poor stars and red is the S-process rich. These are the percentages of magnesium 24 plotted against magnesium 25. And if you can see any kind of correlation here, please let me know because I can't see anything. And similarly for magnesium 26, I can't find any correlation between the isotopes and S-process groups. So what implications does this have for M22's formation scenario? I'm going to take a quick detour and quickly improve upon the errors using differential abundance measurements, which I can discuss at the end if you're interested. But ultimately, this method allows us to reach 0.01 DEX errors, which is about 2%. And this is over 5 times better than previous measurements. This sort of spread in iron and S-process elements is very rare for globular clusters, like Gary said before. So this suggests that maybe M22 has some unique formation history and is possibly a nucleated dwarf galaxy rather than a globular cluster. So ultimately, we have an increase in S-process elements, but also no change in magnesium isotope ratios. And this sounds like a bit of a contradiction, but it's actually really good as it sets a really tight constraint on mass ranges of AGB stars. Let's take, for example, lanthanum and a 3 solar mass AGB star. We can dilute the amount of lanthanum from almost no AGB to completely AGB ejecta. And this red line is just showing the difference between the S-process poor and rich populations. The model intersects with our observations at about 6% dilution, but the trick is that we need to simultaneously fit this with the magnesium isotope ratios as to not see any change between these two populations. And we find that only low mass AGBs are capable of explaining this. And if we take a 3 solar mass AGB, for example, this star has an average lifetime of about 290 million years at this metallicity, implying that there could be some extended star formation happening here. Again, this kind of plays into this narrative that M22 is a disrupted dwarf galaxy rather than a globular cluster.
Maddie, that's 2 minutes.
So, great, at the end anyway. So in conclusion, high precision differential abundance measurements have confirmed metallicity spreads, and isotopic analysis suggests that there is some extended star formation happening within this cluster. So the answer to the question of whether M22 actually is a nuclear dwarf galaxy is maybe. I don't think we can ever really be certain of this unless the dynamicists reconstruct the entire merger history of the Milky Way. But for now, I'm just happy for M22 to be yet another enigma in our night sky. Thank you everyone for listening.
Thank you, Maddie, for a fantastic talk. Do we have any questions? Gary has his hand raised.
Great stuff, Maddie. Quick question. Do you know anything about the sodium, aluminium, basically whether they're first generation or second generation stars are the ones you looked at?
Whether you still classify first generation and second generation when they have an iron abundance spread, I feel like that's a type 1 globular cluster thing. But I'm assuming that the more metal rich ones are going to be our type 2. Well, our second population one, sorry. Is that kind of what you were meaning? Sorry.
Well, I think Fabiola's shown that the sodium oxygen anticorrelation occurs in both iron or S process groups. So I was actually asking whether the specific stars that you've looked at, whether you know whether they're sodium enhanced, for example, or not.
There are
sodium
light
to iron
element,
ratio. So
right. The sodium in the high precision stuff isn't coming out as a perfect correlation that we would expect. So I'm not exactly sure star by star, but I think there are some variations in there, which is something I will explore more in the coming months.
yeah, well, that might have to do with the magnesium isotope ratios. That's all.
Yeah, there's something weird happening there, I think, but in the next couple of years, we'll figure it out.
Okay, thank you.
So we have 3 questions on the Slack, and for interest of time, I'll just ask Luca's question, which is, what are the prospects for extending this work to a larger sample?
Well, as long as you can see the magnesium hydride lines, then you can extend it. But the problem was that David and Fabiola Marino from the 2011 paper looked through every single one of those stars spectra, and those were the only stars that you could see the hydride line in. So it could be done. It's been done in other clusters. Gary did this for Omega Centauri as well. So certainly M22 isn't the only cluster you can do it in, and I'd like to see it being done in maybe all of the clusters that you can get these lines. And if the VLT is going to give us 200 signal to noise ratio stars, then it can be done, hopefully.
Okay. So thank you, Maddie, once again for that fantastic talk.